Again, this is Statistics, DSRT 734 class, Analysis of Variance, also known as ANOVA. So in this lecture, we're going to study about analysis of variance, also known as ANOVA. Our main objective is to use one-way analysis of variance to test claims involving 3 or more means. Also, we're going to introduce two-way analysis of variance. In these lectures, we will not go details about two-way analysis of variance, but again, we're going to introduce it and also how you can use the technologies such as a Minitab or any stat application to find it. So again, this is one of the famous testing method in inferential statistics, analysis of variance. In this case, we can see that we tested a population at least two or one population. Now, anytime, for example, if I want to do a t-test, I can test up to 2 populations or 2 different samples. But anytime we want to test more than 2 groups, in this case, 3 or more, analysis of variance is used. So if I want to test the mean of 2 populations, I may not use the analysis of variance. I may use a t-testing. But again, 3 or more means we use ANOVA. So this is again one-way ANOVA or analysis of variance. It's an hypothesis testing technique that is used to compare means from 3 or more populations. So as we said, again, if the populations are at least 3 or more, we use the ANOVA. If the population is 2, I will use, again, t-test. So analysis of variance is usually abbreviated as ANOVA, or most of the time we call it ANOVA. So here we have a hypothesis. Again, this is an hypothesis testing. So we have hypothesis testing. For example, here we want to test up to K means. So we say that the first population, mu1, is equal to mu2, is equal to mu3, up to mu k. So K tells us the number of populations we are testing. Then over here, we are saying that all the population mean are equal. So if I have a test, for example, three populations, and I said the population mean 1 and population mean 2 and population mean 3 are equal, then my HA will go against it. So in order, again, HA, there's a lot of options here because we can say, okay, mu1 is not equal to mu2 and it's not equal to mu3. Or I can just say that only mu1 is not equal to the rest. Or we say mu3 is not equal to mu1 or mu2. Because here, for example, we have a 3 population mean and we say all of them are equal. So if I'm doing HA against HO, all I need is one of the population mean is not equal. So I have option that mu1 is not equal to mu2 or mu3. Or mu2 is not equal to mu3, but it can be equal to mu1, but it's not equal to mu3. So again, we have a lot. That's why we said HA will be at least one of the mean is different from the others, at least one. So again, this is a one-way ANOVA, analysis of variance. We use analysis of variance techniques if we are testing the means more than 2 populations. So if I'm testing the mean of 3 or more populations, I may use ANOVA. Again, if I'm testing 2 population mean, maybe I may use t-test. So that's the whole concept of ANOVA. So in one-way ANOVA test, the following must be true. We said each sample must be randomly selected from a normal or approximately normal population. And it have to be different populations for each sample. Then the samples must be independent of each other. So they are coming from different populations. And also each population must have the same variance. Each population must have the same variance. So the variation of the data set for all the populations must be almost the same. So those are the 3 conditions. So the first thing we said, one-way ANOVA, to do your test statistics, we find the variance between samples divided by variance within samples. So that's the formula for the test statistics. Again, ANOVA is hypothesis testing. So the same step, we have to state our HO and HA. Always HA will go against HO. Then we have to know the level of significance. Then we have to find the critical value. Then before we do our rejection and also acceptance HO regions, then we do our test statistics to compare. So how do we find the test statistics? In ANOVA, one-way, again, we have two-way and one-way. So this is one-way. ANOVA is the variance between the samples divided by variance within the samples. So the variance between samples, we represent it as MSB, measures the difference related to the treatment given to each sample. So again, measures the differences related to the treatment given to each sample. And it's sometimes called the mean square between. Actually, that's why it's MSB. So MSB is the variance between samples, but most of the time we call it mean square between. Then we also have the variance within sample, which is mean square within. This measures the differences related to the entries within the sample. So we can see the differences related to entries within the samples. Here, the with the between is the differences related to the treatment given to each sample, not within the sample, within the same sample, but that's why it's called between. That's what variance between samples and variance within the samples. So one is within the sample, which is MSW, only the same sample. The differences related to entries within the same sample. But MSB, or the mean square between, measures the differences related to a treatment given to each sample, each. So one-way analysis of variance tests, here we say if the conditions for one-way analysis of variance are satisfied, then the sample distribution for the test is approximated by the F distribution. So the test statistics, as we said earlier, it will be the mean square between divided by mean square within, or the variance between divided by variance sample within. Here we need to know, since we are using the F test, we need to know the degree of freedom for both the numerator and also the denominator. So the degree of freedom for the F test are, degree of freedom numerator is K minus 1, and degree of freedom denominator will be N minus K. Here the lowercase k is the number of samples we have, and the N is the sum of the sample sizes. So degree of freedom for numerator will be, again, the sample, the number of samples we have, minus 1. So if the samples we are using here is only 3, then it's 3 minus 1. But uppercase N is the whole sum of the sample sizes, the whole sum of the sample. So to find the degree of freedom for numerator is K minus 1. Then the degree of freedom for the denominator is the sum of, again, of the sample sizes minus the number of samples we have, which is lowercase k. Again, we're going to do an example soon, so let's go through the steps here. So in words, we say first thing we do, find the mean and also the variance of each sample. So let's say I have 3 populations. I'll try to take a sample of the 3 populations, then find the mean and the variance of each sample. And the formula is given, which is almost the same as descriptive statistics. To find the sample mean, you had all the sample values divided by the sample size. To find the variance, you subtract each value, or subtract the mean from each value, you square it, you sum everything divided by n minus 1. So again, this is a descriptive statistics, the formula we use to find the sample mean and also sample variance. Then here they say find the mean of all the entries in all samples, and that's the grand mean. So I got the mean for each. Now I'm going to find the mean for all the samples. So this mean here is the mean for one sample. So if I have 3 samples, I'll find the mean for each one. I have 3. The next step, I'll find the mean of all the mean samples. So we have a double by here, which will be the sum of all the mean samples divided by the n. Then next, we find the sum of squares between the samples. And there's a formula for this. So SSB between the samples is, again, the mean of each sample minus the mean of all the samples, all square, multiplied by the sample size. For example, if this is the first sample, I'll multiply by the first sample size. Then we go to S2, maybe S2 bar, which will be the second sample mean, minus all the sample means, mean difference square, multiplied by the second sample size. And when we finish up, we sum it together. And that will give us the SSB, or sum of square between the sample. Then we go to number 4, find the sum of squares within the samples. So SSW will give me NI minus 1 times the variance of that very sample. So that will be the variance of that very sample. And here we say NI, because again, the number of samples we have. So N1, N2, N3, etc. So again, we have to find the SSB, SSW. We know the sample mean. Then for each sample, then we find the sample mean for all the sample means. Then we also find the variance. The next step, we're going to find the variance between the samples now. So this is why we find the SSB. Now to find the MSB, it will be the SSB divided by K minus 1, which is the SSB divided by degree of freedom numerator. Then we also find the MSW. So the MSW will be the SSW divided by uppercase N minus K, which is the degree of freedom for the denominator. So now we know the MSB, we know the MSW. Surely we can find the test statistics, which is MSB divided by MSW. Then next, we are going to identify the claim. So we state our null and also the alternative hypothesis. That's the first step. And then we identify our level of significance as we saw in the previous hypothesis testing. It will be given to us. So again, these are the steps of hypothesis testing. Same steps again. Get your HO and HA. Get your level of significance. Identify the degree of freedom. Remember here we are doing the F-test. So F-test means we need degree of freedom for numerator, degree of freedom for the denominator. Then after that, we determine the critical values. F-testing, all I need 3 values. I have the alpha value, the level of significance. I have the degree of freedom for numerator, degree of freedom for the denominator. Then here they say we should use table 7. Table 7 is the F-test table, or the F table. So now I can use the F table again to find the critical value. The critical value will tell me the region between the rejection and the difference on the rejection and accepted HO. So we can, if we know the critical value, we can determine the rejection region. So now we need to calculate the F value, which is the test statistics. Then after that, we will see if the value lies to the left, means we accepted HO. If to the right, of the critical value, then we reject HO. Again, you can see the hypothesis testing, even from the previous F test or chi-square or t-test, they are all the same step. Just that, again, we are testing different variables or different conditions, so the formula changes. So now let's see an example here. So ANOVA summary table, we say it's a table. A table is a convenient way to summarize the result in one-way ANOVA test. You don't need to do this, but again, that's another convenient way to summarize the results in the one-way ANOVA test. So it looks something like this. I have my variations between and within. So I can get my SSB, SSW, the sum of squares, then degree of freedom will be what? The numerator and the denominator. The mean square between SSB over degree of freedom numerator, and within MSW is SSW over degree of freedom. Then we find the F test. This, again, ANOVA have so many formulas, so using this table will help you, or will help us a lot to know the formulas within. So degree of freedom, we know is N, and within is the denominator, etc. So let's see an example. Hopefully this will help us. So here we have an example saying that a medical researcher wants to determine whether there's a difference in the mean length of time it takes 3 types of pain relievers. So that's the key word here, or the key number. We have 3 different types of pain relievers. So here we have to do ANOVA, 3 or more populations or 3 or more samples. So again, a medical researcher wants to determine whether there is a difference in the mean length of time it takes 3 types of pain relievers to provide a relief from headache pain. Several headache sufferers are randomly selected and given one of the 3 medications. Each headache sufferer records the time in minutes it takes the medication to begin working. So the results are shown on the next slide. The alpha is given to us to be 0.01. Now, can you conclude that the mean times are different? So we have 3 different mean values. We want to know if they are all the same or they are different. Assuming that each population of relief time is normally distributed and that the population variance also are equal. Remember, that's our condition in ANOVA. All the 3 here we are doing 3 different populations. So all the 3 populations have to be normally distributed, and also the population variances have to be equal. So this is the table given to us. We have 3 different conditions here, or I'll say populations. Medication 1, medication 2, medication 3. So these are the times, the values for each. So we find the mean for S1, which means our first and our second, we have the mean. Our third, we have the mean. Then we also have the variance for our first value. Again, here we use a descriptive statistics formulas, how to find the variance and the mean for each. So now the solution, we say the K equal to 3. Why? Because we have 3 samples. And N will give me N1 plus N2 plus N3. So first I have 1, 2, 3, 4. The next one is 5, 4 plus 5 plus 4 again. So it will be 4 plus 5 plus 4, which is 13. That will be the sum of the sample sizes. So remember, these are the 2 key values that we are going to use to find the degree of freedom. So K represents how many samples we have. Uppercase N represents the total sample size for all the 3 samples, the total. The sample size for the first sample is 4, second is 5, third is 4. So we had all the 3 values, we get 13. So now we can start our hypothesis testing. The first step, we state our HO. We said they are all the same. Then HA means at least one is different, that's enough. We don't need 2, 3 difference. At least if one is different, then we go against HO. The alpha is given to us to be 0.01. Degree of freedom for the numerator is 3 minus 1 because we have K is 3 samples. Degree of freedom for denominator, we need to know the total of the sample, or the 3 samples. So we have 4, 5, 4, which was 13, minus how many samples? 3, so this is 10. So if I know alpha, degree of freedom for numerator, degree of freedom for denominator, then I can find the critical value. You go to the F table, the critical value will be 7.56. So if it's 7.56, then I will look for my test statistics. So to find my test statistics, we also need this, the mean of all the sample mean. So we have 3 different sample means. So we find the mean of all the sample, of the 3 sample mean. So we had all the 3 values divided by the total sample size, which is 13. So that's the value. Then remember, in order to, again, get the MSB, we need to know the SSB. So SSB formula is given here. Degree of freedom formula is K minus 1. So we can plug in the values and then we solve it. That gives us 10.96. So for example, first we take the first sample. Remember the sample size is 4, so we have 4 here. What is the mean of the first sample and the first value? So that's the difference of the 2 here. The sample size is 59. So you can see 1592, 1592, 4. The same value. We subtract from the 14, the first value, 17, then 4. 1592 is the mean of all the 3 main samples. And that's 15, that's what we find here. Then 14, 17, again, the mean for the 3 samples. So the first sample mean is 14, second sample mean 17, third sample mean 16.5. Then K minus 1, K again is the number of samples, 3 minus 1. So we know the MSB, now we need to find the MSW within. And here also we plug in the value. So it will be the first sample size minus 1 times the variance of the first sample over the total sample size minus the number of samples. So you can see we have 4 minus 1, 6, 5 minus 1, 4 minus 1, 7. Because the first sample size is 4, second sample 5, third sample size is 4. We subtract 1 from each. Then the variance for the first sample is 6, the second 8.5, and 7. So now we know the MSB and we know the MSW. So we can find the test statistics now, which is the F, which gives us 1.5. So now we're going to see if it's on the left side of the critical or right side. So 1.5 is on the left side. So this means we are going to accept HO. So it's true that all the 3 are the same. So our decision say fail to reject HO, which means we accept HO. And here we say there's not enough evidence that at 1% level of significance to conclude that there's a difference in the mean length of time it takes the 3 pain relievers to provide relief from headache pain. So this will take us to two-way ANOVA. As we said, then two-way ANOVA will be our next chapter unit lectures. But here we are explaining in step by step, and also we can use something like a mini tab or any start application. So a two-way analysis of variance or two-way ANOVA is a hypothesis testing technique that is used to test the effect of 2 independent variables or factors on 1 dependent variable. So here I'm testing the effect of 2 independent variables on 1 dependent variable. It's like a, what we call it, multiple regression analysis. I have 2 independent variables. to determine one dependent variable. And here also the same concept. So the first thing, we have example here for gender. We say type of medication. Male take type 1, type 2, type 3. Female take type 1, type 2, type 3. The main effect, we say the effect of one independent variable on the dependent variable. And we want to also know the interaction effect, which is the effect of both independent variables on the dependent variable. So main effect will be the effect of one independent variable on the dependent. So I have S and Y and Z. The effect of X and Z, Z is our dependent, X and Y is what? Independent. So the effect of X and Z is what we call the main effect. Only one independent and dependent. Then the interaction effect means the interaction of both two independent, the effect they have on the dependent variable. So we start with the two ANOVA hypothesis. The hypothesis for main effect will be the gender has no effect on the mean length of time it takes a pain reliever to provide relief. Then our HA will be the gender has an effect. So to go against HO. HO said has an effect on the main length of time it takes a pain reliever to promote relief. Then we can also say HO can be the type of medication has no effect on the mean length of time it takes a pain reliever to provide relief. And if that's the case, HA will go against it, which says that type of medication has an effect on the mean length of time it takes a pain reliever to provide a relief. Then another option, hypothesis for interaction effects. Now we have the two independent against the dependent one. So here we say there's no interaction effect between the gender and type of medication on the mean length of time it takes the pain reliever to provide relief. And HA then will go against it, saying that there is an interaction effect between the gender and type of medication on the mean length of time it takes a pain reliever to provide relief. So the two-way ANOVA test will calculate an F-test statistics for each hypothesis. Then it is possible to reject none, one, two, or all of them. So we can see based on the hypothesis, it's a very long process. So most of the time, two-way ANOVA, we use technology. So here, for example, we can use a technology tools such as Minitype to provide two-way ANOVA tests. So in summary, again, we more focus on the one-way analysis of variance to test the claim involving three or more variants. We kind of also introduce the two-way analysis of variance, how the HO can be stated 3 or 4 times. Yeah. In our question here, we have a main effect interaction. Main effect means we have two independent variables determine one dependent variable. Main effect means you take how one independent will determine the dependent, or how the another independent may determine the dependent. That would be the main effect. The interaction effect means we are using all the two independent variables. We want to see the effect of the dependent with the two independent variables. So again, wish everybody the best and see you in the next lectures. Thank you.